Hello and welcome to the Statistics Walking Talking Mock. I would suggest that you take notes as we go through these questions, and then when you are happy that you understand everything, then take another copy of the exam paper, test yourself and see how you get on. If there's elements of those questions that you're not sure about, then please do check back in with us and we will help you. Let's get started. So some simple Venns to get us going on the stats paper. And first of all, finding the probability of A. To be honest, that's kind of a GCSE level question, so it should be a nice opener for us all. We essentially just want to see what the probability is within that ring A, and so therefore adding together the 0.13 and the 0.25 to give us 0.38 in total. So the events B and C are independent, so a good idea when you see things like that given to you is to write down the independence criteria there. If they're independent, then the probability of them both happening, one doesn't affect the other, so it's simply going to be that. And so the aim is to find out the value of the P and Q. So let's find out where they are. Okay, so the outside bit and then the bit within C. So it makes sense, I guess, given that we've been given the fact with independence, to proceed using it. So the probability of B and C, of course, is this overlap here, so 0.3. Probability of B would be the sum of those, so 0.25, 0.3, that's going to be 0.6 for the probability of B, and the probability of C there is going to be 0.3 plus P. Be really careful with the use of brackets there. That's likely to go wrong if we don't. Okay, so then just solving that, P's are unknown. Half of 0.6 is 0.3, so that gives us that's simplified, and so P is 0.2. The Q must be one, take away everything that we have there, so thinking with that being a 0.2, then the Q is just simply going to be 1, take away the sum of all of those, so 0.38 because I've already added those, 0.05, 0.3 and a 0.2, and if you calculate all of that you get 0.07. Whoops, try again, 0.07. Last up, find the probability of A given that B doesn't happen. So very much there we've got our conditional probabilities, and if the question is very formulaic in nature in terms of the way the values are given, I probably err towards using the formulae. If my information is given on a Venn diagram, then my preference would definitely to be doing it with that sort of zoom in effect of doing it on the Venn. So let's have a little look. We want the probability of A given that B doesn't happen. So we only want the probability on our Venn here of this, because we can't have this bit here because that's within B, isn't it? So therefore, the probability of A without the B is 0.13 out of anything that isn't in B. So therefore, let's tick off that one's a not in B, that one is a not in B, and that one is a not in B. So that zooming in effect, I'm just going to kick out the ones, anything that is in B. And I think rather than sort of being too reliant on a formula, I'd rather just do it visually from the diagram there. Conditional probability from a Venn tends to be the way forward. So your answers that you can have there are either 13 over 40 or the decimal equivalent. And there we go. There's our first 6 marks. Looking at the examiner report for this was a positive start to the paper, positive and accessible, so that's saying that most people did pretty well on that. If there were issues, it was with Part C, conditional probability. And they do suggest, actually, like I did, that we do it via a diagram. That was a more successful way to do it than via the formula. And the only other concerns, if there were them, was not using the independence. But that's one of those basic conditions that we need to know off by heart, please. So I'm looking to decode this question. You've got machine filling packets with sweets and sometimes a prize. They're put in boxes delivered to shops, 40 packets of sweets in a box. I'm already, when I'm trying to think of the distribution, that looks like a fixed number of trials when you've got that 40. So I'm already erring towards thinking that. Read a little bit further. You've got a random variable, stated condition needed for it to be binomial. Okay, so it's looking like it is. So a condition that's also needed for this to be modelled with binomial is that the prizes are packed at random, so the probability remains constant. You're told that the number of trials is fixed, so therefore that wasn't allowed in the answers because it's stated condition needed. Well, you've already got that, so it's another thing that's needed. So something about the probability being constant, the prizes packed at random. Lots of people lost marks for talking about the trials, which is already a given. That's how I managed to identify it as binomial in the first place. So packed at random, probability of getting a prize is constant between the boxes there. Okay, so we've got this lovely distribution. It's looking rather binomially here. There we go. And just a nice sort of opener into doing some calculations. First one, the probability that t is exactly 6. So always summarise what you're after in probability notation, even though I totally admit that this then is a case of chucking it into your calculator. So that sort of thing. And then if you read the instructions on the front of the paper for stats, it says 3 significant figures unless otherwise stated. And as I've noticed with the mechanics more recently, they are definitely penalising rounding not as stated. All right, and they did again here. So in previous years, if you look at mark schemes from other years, they never really cared it particularly. As long as it rounded roughly to the right thing, it was fine. They are definitely clamping down on that, so do follow the instructions. Part 2, probability that there's fewer than 3. Fewer than 3, so write it down as described. Obviously then we need to adapt that for the way in which the calculations occur. So that stage is pretty important too, I'd say. And then, of course, it is a throw it into your calculator and off we go. So getting our values there, following the instructions. I should give you a little bit more. Values given. Okay, on to part C. Camille Sweet Shop buying 5 boxes of these sweets. Find the probability that exactly 2 of these 5 boxes have fewer than 3. So there you go, a classic statistics sentence, isn't it? Exactly 2 of the 5 boxes have fewer than 3. Let's decode this. Look at what happened in part B. That we've just worked out the probability that a box has fewer than 3. So that is a followed through thing. So let's think about the distribution for Camille's situation. That's why I've cunningly called it K for Camille. Well done me. So again, it's binomial. Why? Because it's a fixed number of trials with the 5 boxes. Probability of success this time is having fewer than 3 packets containing a prize. So therefore we go back to what we have just calculated just up there. So then what do we actually want? Exactly 2. So write down the probability that we required. Again, you're showing that you've decoded what you needed to. And we are at the point here where we can pop that into our calculator. Nice. It's worth noting here that should you have got the part B wrong. So if that probability wasn't right here, but you correctly used it with workings in part C, you get the marks. Whereas if you didn't do any workings in part C and obviously came up with the wrong answer because of part B being wrong, you can't gain the follow through marks. So it's just a little bit there in terms of the way the mark scheme works. Obviously, every maths teacher in the land always says, show you working out. But if you don't show you're working out in part C and you've carried through a wrong probability, you get no marks. If you show you're working and show exactly where you've used it, you can get your method mark. Okay, so low risk strategies again, folks. Make sure that you show you're working because should it go wrong, then we're going to minimise the loss. And on to part D, looking very hypothesis test there. As soon as someone's claiming something, we reckon that's the likely to be the topic. Notice that the claim is that it's less than a seventh, so that gives us an indication. Hypothesis test, one-tailed test, because he isn't just claiming it isn't a seventh, it's specifically that it's less than. We've got a sample of 110 packets there, so I guess we need to be aware with our distribution for our binomial that we've got 110 is our sample size, our fixed number trials or whatever. 9 packets contain the price, so that's our observed experimental data value, isn't it? 5% significance level. Right, I think I'm good to go. I know what I've got to do to proceed. So very structure driven, isn't it? Hypothesis testing. You know, first thing is to give the null hypothesis, the alternative hypothesis, and our highlighted thing. Whoops. Waterfall. Our highlighted thing there shows that we know it's one-tailed and a less than, so I've already made that decision when I start writing. Good idea to make sure we're very clear on the distribution. It's had a bit of a switcheroo a number of times through this question. Look how this has evolved, I suppose. You've got that T version, you've got happen to Camille, and then you've got the hypothesis test situation. So it really highlights the importance of summarising the distribution that you're using for every single part of the question, because for 3 different parts, it was 3 different binomials. Yes, it was all binomial distribution, but the number of trials, the probabilities, everything is varying each time, so summarise carefully. Looking at our observed piece of data, 9 packets contained a prize. So under these conditions, what is the probability of getting 9 or fewer? How fluky a result is that? Is the question I'm asking myself. Well, under that binomial distribution that I've just stated above, then the probability of that is 0.038 and so on, which is less than, going to significance level now, is less than the 0.05. So that's saying that it's quite unusual, isn't it? So what does that mean? Well, that is a very unusual result if that was the distribution that we have. So I'm going to reject H0, that there is significant evidence to suggest the proportion of the prizes is lower than a seventh. So reject H0, evidence to suggest proportion of prizes is lower than a seventh. So we've got our overall conclusion, reject, accept H0, H1, however you want to word it, and then put it into context. You could have said Camille's claim is allowed because he claims it's less, that's what he thought was happening. Looking at the mark scheme, they were really strict actually, interestingly, about wanting the word proportion there, so not the number of the prizes, the proportion of the prizes, because of course that's what that seventh is suggesting. So what did the rest of the world do on this? It was Generally, it was a well-answered question. The only places really where it fell down were part A and the rounding. Generally, it was quite well answered. Hypothesis testing in this sort of context is now being answered quite well. It's quite a strong topic for quite a large number of candidates. And we turn the page and see information about total rainfall, and we go, oh joy, it's the large data set. It's going to be there, folks. We know it's going to be there. It's not going to be loads of marks, but it is going to always be there, and it's going to be worth some marks. So it isn't one that I'm suggesting that you spend hours and hours revising, but I do think you should familiarise yourself in the week preceding the stats exam. Just what sort of values are there? What are the, for each of the types of data, maximum, minimum, so the sort of general ranges? What are the units? Where are the weather stations? You know, which ones are up north or down south within the UK? Knowing the anomaly of where in the world things are in terms of summer, winter, the data being from May to October, all those sorts of things. Don't spend sort of days and weeks on it, but just have a bit of an idea should be enough. Okay, so part A, explain how the data will need to be cleaned before Ben can start to calculate statistics such as mean and standard deviation. Well, even if you know nothing about the large data set, clearly, if I'm trying to find the mean from this group data, trace is not something that I can use. Okay, so therefore I need to do something with that. Now, the wrong answer to that is that you replace those pieces of data, because if you replace them, then essentially you're not including any of the days where there was just a very tiny amount. All right, so that can't be the answer. This is where you have to have a bit of knowledge of it. You should take a value. It traces between 0 and 0.05. Okay, so this is 0 to 0.05, between those values. Clearly it's not 0, otherwise I'd be in that group there. Okay, so it's between those. So we need a number that's going to represent that. We're going way back to when you did mean from a frequency table, a group frequency table. We tend to take a midpoint, don't we? Okay, so therefore, something like for part A, replace the trace with 0.025, i.e. halfway between the two, is what we're after there. So it must be replaced with, the trace needs to be replaced with a value rather than those 29 data points being replaced with something else, because that's going to warp your data and not be representative. Hopefully part B could be nice and strong topic for us there. So some of the work's been done for us. So we've got the sum. Therefore, if we want to find the mean, then it's all of the data points added up. Thank you very much. You gave that to me, 390, divided by how many there are. Looking through, using all 184. I mean, that's a bit of a hint, isn't it? That you have to use all 184, not a sort of replaced version. So if you weren't sure about part A and then you moved on to part B, maybe that gives you a little bit of a shove in the right direction. Here's hoping, eh? Right, so 2.119, but I've got to follow the instructions of 3 significant figures unless stated. It doesn't state, I'm just doing a double check. Don't want to be losing any marks or rounding because that's just rubbish. Okay, so standard deviation. Then I want the sum of the squares over the 184. Yeah, minus the mean squared, all square rooted, because that would have given me the variance. So thank you very much. You've already told me the sum of the squares minus the mean squared, all square rooted, to give us 4.367. Follow the rules of rounding. Nice bookwork question, and unsurprisingly that was very well answered. So Ben suggests using the statistic calculated in B to estimate the annual mean total rainfall and leaming. Using your knowledge of the large data set, well, we've just discussed that, haven't we? What you need to know for that is that the data is from May to October, isn't collected. It's May to October, yeah? So, not suitable for whole year. You'd have guessed in Leaming it's going to be a bit wetter in the winter months rather than May to October. You don't need to write all of that. That's absolutely fine for that. And state given a reason. How do you expect the estimate in B to differ from the actual? So the actual is likely to be more, as I've just said. Actual mean likely to be higher as it includes the winter months. So that's just testing you aware which months this data was collected from. So with a little bit of knowledge and a bit of common sense there, hopefully that isn't as challenging as we sometimes fear. Certainly known trickier questions to decode. Study was made of adult males in the country. It's found that the heights were normally distributed. I'm reckoning this might be the normal distribution question, folks. So, proportion of men that are taller than 180. Do we have full details of the distribution? It certainly seems so, but we're going to follow good things, which is to do our summary before we jump in and do any calculations for any distribution. Always be clear what distribution we're using. So, what do we want? Probability that the proportion are taller than 180. So again, I'm summarising the probability that I was attempting to find, and I do then admit it is chuck it in the calculator, off you go, and then 0.249 first mark gained, happy days. Student claimed the mean height of men of region B is different. A random sample of 52 men from the region had a mean height of that, so they've actually done some experimental thing. Student assumed the standard deviation was that. Suitable test. So again, decoding this, this seems to be heading very much towards a hypothesis test on the normal distribution. So, follow the rules. The initial reckoning is that the mean is 175.4. Student claimed that the mean height of men from the region of this country was different. Not saying higher or lower, so therefore my reckoning is that suggests we've got two-tailed test. Always a bit of a tongue twister, that one, isn't it? So therefore, if it's different, that's not equal to two tails. So I'm already having a little look-see down, 5% significance level. I'm already thinking along the lines of cutting that into 0.025. So we're thinking our way through. Right, what is our distribution for this? Well, we have a sample from this data. So therefore, if you're taking a sample of data, your how varied this data is going to low. So we need to adapt our variance because of the sample. So we are using, of course, the same mean value, but we've got to adapt this variance to that over root, and the sample size was 52. So again, it's following those same patterns, isn't it, of stating the distribution. Then we're going to do some calculation of the probability. So we take our observed experimental data there. What's the probability that it's that or more extreme? So we go with that, 0.028 and so on. then the important thing is that is a greater number than our significance, because remember it's two-tailed. That is greater, so therefore it's not as unusual as we may think. So the student's claim is not supported. Notice if we hadn't spotted it was two-tailed, then we would have drawn a different conclusion. There are marks awarded for, even if you didn't spot that it was two-tailed, you would get some credit for adapting the normal distribution, all those sorts of things. So it's not a case of wiping out and losing everything if you don't spot that particular thing. So, insufficient evidence to reject H0. So the student's claim that it's changed is not supported. Okay, on to part C. Find the p-value for the test in part B. If you look all the way through your edXL endorsed textbooks, they don't talk about these p-values. So it is a tiny little bit of the spec that they haven't even put into the textbook, but it is actually there. Consequently, funnily enough, there was only a handful of students across the country that got this right when it was in the exam. What a surprise. So what is a p-value? P-value is the probability that if you take a value from this distribution, so you take another piece of data, that it is as extreme as your observed value. Okay, so it is at least as extreme as that value that you have, the observed data that you've already got. Okay, so what is the probability of it being as extreme as we had in our observed data? Well, that comes from this calculation here. So if I was to pick another piece of data, so observe another piece of data, what's the probability that it would be as extreme or more extreme than that piece of data? If it's one-tailed, then it's going to be that value. But of course, it could be extreme the other way. So therefore, it's because it's two-tailed, it's two lots of that. And so therefore, it's our probability times 2. It is important that you don't use the truncated version that I've got there, that you use the full value. Obviously, premature rounding can lead to lost marks. In this case, less so, more the fact that people didn't have a clue what a p-value was, to be fair. Okay, so nice and simple as long as we know what a p-value is. And the good news is we do now. Not loads to report from the exam report mark scheme here. As I say, if you did it as a one-tailed test rather than a two-tailed, then you could have got 3 out of 5 for the parts B and C together. And as I say, the completion of part C was shocking across the country. So obviously that bit wasn't, the previous part wasn't great. And then we get to part question 5. And I think less than 10% of candidates across the country in this question got anywhere with it at all. So that equates really to examiner mess up, because they don't want everybody to wipe out, because you haven't essentially learnt who's better or worse at statistics, have you? And it's on one of those questions where we'd hope would be quite nice, are discrete random variables. In my experience, they are being a bit fancier with the context. I think because it's a slightly easier topic potentially than the normal distribution, they're going fancy with the discrete random variable. How do I know it's a discrete random variable? When I've got my data in a clear table like that of discrete values with some associated probabilities, then that must be the topic. Right, so let's jump in and get started. Tisham's playing a game. She has a ball, a cup and a spinner. Wow, that makes a change. Normally it's just a spinner, isn't it? To play the game, the spinner is spun to obtain a value of x. She then stands x centimetres from the cup. Okay, so that spinner must have those four values on it, right? So 20, 50, no idea which is bigger and smaller. I'm just doing it to try and get my head around what's happening here. So she spins a spinner, that's the number of centimetres. So you spin the spinner, it comes up 80. So then you stand 80 centimetres from the cup, and then you throw the ball into the cup. She must have a lot of time on her hands to be doing this, right? So the event S represents the event that Tizam successfully throws the ball in the cup. Okay, success is getting the ball in the cup. I can cope with that. To model the game, she assumes this. That's not assumptions that go through my head. I don't know about you. So let's actually find out what this is saying. So the probability of success, given that she is that distance from the cup. Okay, so those probabilities are, it's K, constant, we don't know it is, over, so the probability of success is K over 20 if I'm 20 centimetres from the cup. It's K over 100 if I'm 100 centimetres away. Kind of makes sense. Further I'm away, then it's harder to throw the ball into the cup. Fine. And also, the probability of success and getting that particular value should be the same whatever the value of X is from the spinner. So we have got something that is constant there. I think I'm going to have to put that into a value of saying, okay, so the probability of success if I am 50 centimetres away from the cup is the same as the probability of success if I'm 80 centimetres away from the cup. Right, but it's definitely harder to get that in if I'm further away. So what must be the case when I'm thinking about these probabilities here, that must be the other way around, mustn't it? That therefore it's more likely that the other things come up. So an overall success rate, you've got to think of, well, how likely is it that I get that distance, as well as the probability of throwing it in when I'm at that. Okay, so there's lots going on there. It is not a surprise that this didn't go too well in many cases. Show that C is 8 over 5B. So B and C are for the 50 and the 80, aren't they? So the probability of success and kind of rolling the 50, if you like, is the same as success at throwing and rolling an 80. So that's kind of what it's getting at, is success and rolling, it's not rolling, it's spinning to get that particular number. Okay, so therefore I've got the probability, I suppose, of for B, so what is the probability on my spinner of getting the 50? So that would be that piece, wouldn't it? And success, when I am 50 centimetres away, is K over the distance, or that 50 there. Similarly, the probability of being 80 centimetres from the target is C. The probability of success if I'm stood there is K over 80. There's hope here because I think the K's are going to cancel, are they not? So therefore, B would be 80 over 50. B times 80 over 50 would be C, and I can see there, happy days, that cancels to what I want. It's not the algebra there that's tricky. It's this interpretation here of success when I'm stood there, and what's the probability that I am actually stood there in the first place. So spinning each of those things fixes where I'm stood. So what's the probability of me being stood there, and success once I'm stood there. So part B, find the probability distribution. Now that is something, regardless of this rather odd context, we need to know what that is. You want the but if you ask for the probability distribution, essentially that's your probability distribution. It's find each of those probabilities. So using the same logic, if I roll B, my probability of getting it in is that. If I roll A, then the probability is going to be K over 20, because that is the one that corresponds to being 20. Similarly, the one that would correspond to 100 is the D, so B times the K over 50 would be D, probability of being stood there, times the probability of success when I am stood there. Let's tidy this up. So A would be 2/5 B and D would be 2B. And then finally, we use the most obvious bit of information that we always know about a discrete random variable is that if you add up the probabilities, you get 1. So what are our probabilities? Well, A is 2/5 B, 8/5 B, and 2B, so each of those must equal to 1, and combining those all together you will find that B works out at being a fifth. But we were asked for the distribution. Easiest way I think to communicate that is to just pop it into the table, to be honest. So for 20, A is 2/5 of B, so 2/5 of that is going to be 2 over 25. We know the B already is a fifth. For the 80, we want the C value, so that's 8/5 of B, so that must be 8/25. And then for the 100, it's going to be 2 lots of B, so 2/5. Whoops. Let's just go with our logic. What it says for that second bullet point is that the probability of the success and actually getting those things, each value remains the same. So, and we've already decided, well, the further I am from the target, the harder it is to get it in. Therefore, to compensate for that, it must be that it's more likely that you get the 100 and so on. So I would hope in sequence these are getting bigger, and that's certainly the case, isn't it? That 2/25 is the smallest probability, combined obviously with the easiest throwing situation, all the way up to the 100, which is the hardest thrown situation, but because it's easier to get it on the spinner, that's what maintains the probabilities. Okay, so part C, we've got that the Nav has tried a large number of times to throw the ball from a distance of 100. He successfully gets the ball into the cup 30% of the time. So the probability of the success of the actual throwing bit is 0.3. So 0.3 is the K over 100 value, which I reckon implies that K must be 30. So that K value, if we look at that piece there, the probability of the success from each of those distances, so it's the K value over the distance. Well, if my distance is 20, then that probability from there would be 30 over 20. Well, you can't have a probability over 1, so therefore it falls down because of that, doesn't it? So overall, a super challenging question. As I say, it sort of failed as a question from the exam board point of view because people just couldn't interpret what was going on. I think people thought that the K over X part was feeding into the A, B, C and D, and it wasn't. It was the fact that you've got two probabilities going on here, the probability of throwing it in successfully and the probability of getting that distance from the spinner, and that just was an interpretation too far for most people. So if you survived the nightmare of question 5, then the final question of the paper actually was a lot more accessible, sometimes rather bizarrely, I have to admit. Okay, so we're back on familiar ground, histograms. Let's just have a little look at the context, because sometimes later parts do rely on that. So it's all about a medical researcher looking at the number of hours a patient stays in hospital for following their operation. Okay, they've looked at 90 patients, and we want to use the histogram to find out the probability that a patient waits or stays in, it's not that necessarily waiting their recovery, I suppose, between 10 and 30 hours following their operation. And that is something that would be a sensible thing for hospitals and the NHS to look at, because when you're looking at bed management, putting in scheduling different operations, you want to know on average how long people are going to be in hospital, because that bed's being cleared before you not going over capacity and those sorts of things. So it's actually quite a good context, rather than chucking the ball in a cup in a weird way. Anyway, let's move on. Let's get over that, shall we? Right, so for part A, we want the probability that the recovery is between 10 and 30 hours. So it's going to a good old solid histogram question that we want. You've got 90 patients, so it's going to be out of 90, isn't it? But let's find out how many patients fall into that. So always this sort of stuff, I'd be looking at my diagram there. So that first box, so this piece here from at that height there was be looking at the scale there. Every 2 small boxes there on that grid is equal to 1, so therefore that's 2 times, and then it's 1 for every small box going upwards, so 2 times 4.2. Just be super careful about the scale before you jump in with that. You don't want to be losing marks on that. Okay, you're going for that next block that's a height of 4. What's the width of that block? That's also 4, so 4 times 4 plus 4 times, it's the same width, isn't it? That looks like 3.5. And I'm only going up to there, aren't I? So that's definitely width of 10. That's a nice easy one to finish. So 10 times 1, add all that up, then that comes to 48.4. But remember, it is a probability that we're after. So just me writing that down reminded me, because I've sort of gone into the throes of the calculation now. Actually, don't lose sight of what we were doing. Then we've got that, haven't we? So it's a probability that we need. And actually reading the examiner report, that is what trips some people up. They perfectly got the 48.4 and they've lost sight of the fact it was a probability. So that's daft, isn't it, to lose the final mark in that way. Again, they penalised that not following the rubric, as it's called, the instructions, rounding to 3 significant figures. 3 significant figures unless otherwise stated. Okay, next part, reference to the histogram, state with the reason whether or not Tom's model would be suitable. So what was Tom's model? Normal distribution. Does that look like it's a normal distribution? What am I looking for? General shape of a normal distribution, like that. Okay, it's not going to be in a smooth curve because it's a histogram, but we know that the normal distribution is symmetrical. So no, it's not symmetrical. And interestingly, that was really badly done. There's people talking about sort of continuous data, all that sort of thing. Well, it is continuous data. That's not the issue there. The issue is the fact that we want a symmetry of our distribution to even start thinking about modelling with the normal distribution. Part C is possibly the weirdest question I have seen on a stats paper, and that's including that silly one about chucking things in a cup. So we've got a possible distribution here of y is kx e to the minus x, because the normal distribution would be rubbish there because it isn't symmetrical. So, okay, let's look at other options. I'm happy with that. X is the tens of hours. Notice how that is in bold, and that can come and bite us if we don't take note of that later. K is constant. Who knew? Use algebraic integration to show that. So this threw me when I first looked at this, because it's the reason why it's the weirdest stats question in the world is it's not a stats question. It's basically saying there's an integral, integrate it. So it's not a weird question, it's just a weird stats question, because all we're doing is doing our good old pure maths, aren't we? So I've already made a start while I'm talking to you here. What have I decided? I've decided it's a classic integration by parts. X e to the x, or x e to the minus x, is one of those classic integration by parts. Why? It's a product. It's not a recognition, and I know by differentiating one of those pieces, i.e. the x, it makes it nice and simple, and the other one is very integratable, my word. Therefore, it absolutely jumps off the page to me that it's an integration by parts. Depending on your levels of confidence, if you're not super confident with it, then write down the integration by parts formula. If you're fine, then just go for it. So our uv will be minus x e to the minus x. And I know here I've got to be super careful. So normally the integration by parts is, I'll be going minus the integral of. However, I've got a negative sign here, so therefore that's going to turn that into plus the integral of e to the minus x dx. So when I'm doing my v du dx. So carrying out that integration again, and I'll be ready to put my limits in by that point. So I'm going to go for my square brackets. Again, got to be careful. I wasn't, because I was chatting away as I was doing it. When I integrate e to the minus x, I get minus e to the minus x. So therefore, I've created another negative. And it's probably of no surprise to you that it says on the examiner report, issues with signs there, or some people being confused because it wasn't a stats question, perhaps. No, that's just me. Okay, so you're doing our usual substitution in of the limits, e to the, that's going to give us a 0, minus, so plus 1. And is there a particular format that we're asked for? Yeah, it's used to show that. So at this stage, I've got a positive 1, so I'm getting hopeful there. And then we're clearly going to take out the negative and the minus e to the minus n, so that will be an n plus 1, and we've got what we wanted by using no statistics at all. How strange. So let's start using the model. There are 90 people in the study, are there not? Remember, I said it was worth reading all this story at the top. So it's from a random sample of 90 patients. So therefore, if we're integrating where the model is, so from 0 to 4, then substituting in n equals 4 should give us a total of 90, because that's all the people. So k 1 minus n plus 1 e to the minus 4 is 90, and so therefore we've got k1 minus, that's 5 e to the minus 4. So that gives us a k value of 99 point, and a mess. Going back to, we want the nearest integer, so k equals 99. So using some of the details of the model, so it being valid from 0 to 4 and the fact there's 90 patients. Okay, next up, we're focusing back on what is happening from finding probabilities from 10 to 30. So first of all, we want from the model where we're using the flawed normal distribution. So from that, we can just use our calculator. So the probability that the recovery time is between 10 and 30, we can just get that's 0.649. And then we want the alternative model. Running out of space, so I'm just going to do it over here. So it will be 99. I've got to be careful there because remember the tens of hours. So I don't want to put 30 and 10 in. I need to put the 1 and the 3 in. So it's 99, and then substituting, I want 1 minus 3 plus 1 e to the minus 3 minus 1 minus 1 plus 1, not 10, e to the minus 1. And therefore we get the 1's cancel, so the 1 take away 1, and therefore we've got 99 lots of 2e to the minus 1 minus 4e to the minus 3. So that gives us 53.12. But we want a probability, so the same thing as we were saying when we were doing the histogram actually. So our probability of 10 to 30 is that value that we've calculated over the total number of patients. So that is 0.502. Follow the rounding rules, becoming a habit now. There we go. Okay, so a limitation of the model. So this is the model there. It's up to 4, so that suggests 40 hours. Well, there are plenty of operations where people stay in for a couple of days or more afterwards, isn't there? So the limitation is it's only valid up to 40 hours. So as soon as you go below the 40 hours, then this is going to be a bit flawed. Okay. Right, so how well done was this question? As I say, part A was fine as long as you remember to do the probability. The integration by parts, the non-stat stats question, was fine apart from the odd issue with signs. Part E was generally well answered as long as you realised you needed to use 3 and 1 rather than 30 and 10, and rarely correct, to be fair. For part F we didn't see the limitation, but what's going to help you to see the limitation, I said read the start of the story. So even if you'd forgotten the story and you're asked to sort of see where the model might be flawed, my top tip is go back to the original bit, the medical researcher, blah, 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 because then that puts you back in the context of the problem and may help you to do that. Generally, this was quite a challenging question, and I guess not as challenging as question 5, but even within this quite challenging, certainly in the integration by parts, there's some, interpreting a histogram, doing a bit of normal distribution. I guess there was lots of different things. The thread to it didn't flow nicely, so that makes the decoding trickier. So that would have been why it's quite challenging. So have a think through all of this, and when you feel confident with it, see if you can recreate it on a new copy of this. And of course, if you're not sure about anything, please ask us. Thanks for listening.